Okay, we are the conveners for this next session. I'm Kirsty Tinto.
I'm Brendan Eckerman.
I'm Julie Andreasen.
We have a very exciting session that's going to span the atmosphere and the ocean and the ice as they interact with each other in a fairly sensible order. We have 7 speakers. We have Brendan is going to be keeping the speakers to time. Speakers, you should know about that. And we're going to have 10 minutes for each speaker. We're going to try to save questions to the end of the session. So if you think of something and you really can't concentrate, if you don't have this answer, then do put your hand up. But otherwise, note it down and have a think as you listen to the rest of the talks. Does this relate to anything that anybody else says in the session? Because these talks are all connected to each other in interesting ways. So at the end of the session, when we have the discussion, it would be great if everybody who has questions in the room lines up at the microphones on the steps. And if you can ask questions that can go to more than one person, then that would be a really good way of fueling the discussion. What else?
I'm going to keep an eye on the Slido as well. Presenters, yellow is going to be your 2-minute warning. That's about all I've got.
And I thought you were going to remind me that we have lots of students. So students, be careful to alert us to your presence so that people can give you feedback on your presentation. Thank you. Okay, the first speaker is going to be Garrett Finucane, who's coming up now and will be speaking on buoyancy gradient-driven flow of warm subsurface waters into geometrically complex ice shelf cavities. And we're all looking forward to hear it.
How do I point? This button?
And then go over that way a little.
Oh. There. All right. All right. Hello, everybody. My name is Garrett Finucane. I'm a graduate student at UCLA in the Atmosphere and Ocean Sciences Department. My advisor is Andrew Stewart, and that's who I did all my work with. So yeah, we're in Antarctica. Ice shelves around Antarctica are melting at really different rates. We all know that, and we know that a large part of that is due to ocean-driven melting within the ice shelf cavity, but we don't really, from the ocean side yet, have a quantitative understanding of how things like the geometry of the cavity, the surface forcing over the ocean, offshore stratification translate to melt in general. And we don't know that because ice shelf cavities have a lot going on. So in the ocean, we have sea ice, there's katabatic winds careening off the ice shelves, there's polynyas, which create dense water, and ice shelf cavities in real life are really confusing 3D shapes. And that makes it hard to build like this mechanistic understanding of how hot water gets in and drives melt. What we do know matters is hot water, and principally circumpolar deep water, which is this water mass that lies at depth off the shelf in Antarctica. And it's at different heights at different ice shelf cavities. And that means that it has to kind of get on to the continental shelf to reach the ice and drive vigorous melt. And so our goal is to build a general understanding of what drives these warm water inflows and therefore melt in ice shelves of any geometry. Yeah, and so a hard first step to that is finding the temperatures of the deepest waters that can actually get into the cavity. And this is like a really classic problem in parameterizing ice shelf melt from offshore hydrography. So if you have some point like marked in green here and you want to know the temperature of the water that can get in, there's a few approaches. I have this depth temperature cast on the right. So you could just do the depth of the point. You could do the depth at the ice edge, or you could do the sill depth, although the sill depth is really easy to define in 2D. It's a little bit more confusing in 3D. And if you do that, you get 3 really different answers for the temperature of the water that's getting into these cavities and is reaching the grounding lines. And so we wanted to do better. And so we came up with this new thing that we call the highest unconnected isobath. The highest unconnected isobath is the shallowest depth for each point on the continental shelf at which that point is unconnected to the open ocean on an isosurface of depth, which is a really hard to understand definition. So I'm going to talk it through in 2D. So if we go back to that picture we were looking at just before, we're going to look at this grounding line point again, and we're going to think about how we could get at that sill depth I talked about. So we can start, ooh, I think a window popped up. So we can start at the depth of the point, and we can ask, is this green line, is it connected to the open ocean? It's not. So we can go a little bit higher. It's still not connected to the open ocean. Even higher, and if we were to go any higher from here, we'd be connected to the open ocean. So that right there, that's the hub depth in 2D. In 3D, I made a little diorama for us. You're going to pretend this is an ice shelf cavity. At the top left, that's the grounding line. There are these 2 points we're going to calculate the hub for, those 2 gray points. And you're going to imagine that we emptied the ocean of water and we're filling it in from the outside in the absence of dynamics. So these 2 black points, they're at the same depth, but as we pour in water from the outside, it fills, it hits the point on the left, but because there's a sill on the right, the water takes a lot longer to reach it. And so that's the hub for those 2 points. Here on the right, I have a picture of the Filchner-Rhone, and you can see for that point X at the bottom and just a lot of points on the Filchner-Rhone grounding line. At the red contour, they're connected to the open ocean, but by the green contour, it's disconnected to the ocean on an isosurface of depth. And so the nice thing about the hub is all you need to calculate it is some bathymetry, and you need to know where the ice is so you can mask that out, as I've done here. It's really fast to calculate. It takes under 5 minutes to calculate for all of bed machine 2. And it has a rigorous topological definition. So like mathematically, we know what we're dealing with. And so I'll show what it looks like in bed machine 2. So here's bed machine 2. And we'll calculate the hub, and it looks really boring. It looks kind of like the bathymetry before, and that's because really what we've done is like we've gotten rid of some details, right? Because we're, yeah. And so you might think, oh, well, Garrett, don't be so hard on yourself. It's just the color bar, and it's really boring in any color bar, except if you use a random color bar. And what you get is these psychedelic kind of Rorschach blots. And so what these blobs represent is regions inside each of these ice shelves that are all behind one hub, one bathymetric obstacle, right? You know, in a complex ocean, water doesn't follow isosurfaces of depth, but you can kind of think about it like these are the dominant sills, at least in bed machine 2, that block ocean waters from reaching these points on the shelf. And so if you're familiar with these ice shelves, you might see kind of familiar shapes, right? Like the Filchner-Rhone, it's blocked at 600 meters, and you can see that at the very top right of that dark blob, that's the Filchner trough, I think. Yeah. And so these are at different depths around Antarctica. And so basically what we did is with this hub in hand, we came up with a new parameterization. And I'm not going to go through it in the interest of time, but there's some thermal terms about the temperature at the hub, the temperature of that deepest water that's getting in. There's a term about the slope of the ice shelf. And basically what it's getting at is the buoyancy-driven flow of that CDW into the ice shelf cavities using the hub depth. And it really differs from previous parameterizations because we don't really think at all about what happens at the ice. We just used kind of like this buoyancy argument to say whatever hot water is pushed over the hub into the cavity is used for melt. And so this parameterization, we have this new generalized model, model, and we try to make it as easy as possible for the parameterization to do well. So there's no sea ice, no surface buoyancy forcing. There's an ice shelf. It's a static ice shelf, but it has, you know, melt. It's a 2-kilometer resolution, but it's a pretty small domain, and that means we can run it with a bunch of different geometry shapes and different geometries. So we have different shelf widths, different shelf depths, different ice shelf extents, kind of different looking slopes, different grounding line depths, all with little different random perturbations on the bathymetry. And so then if we take that and we apply our parameterization, we get a pretty nice correspondence. So on the x-axis, that's the predicted melt from our parameterization, and then on the y-axis is the diagnosed melt from the model. And each one of those points is a simulation with a different geometry and a different height of hot water. And so that is nice. It seems like we're doing pretty well at predicting melt. But the question is how it does in the real world. And so what we did is we took bed machine 2 data again to calculate the hub all across Antarctica. We, as our observed melt, we used a Dusimili et al. 2020s basal melt estimates for ice shelves across Antarctica. And then we use World Ocean Atlas hydrographic casts from the 1,500 meter isobath, which is pretty far out onto the continental shelf. And we're going to try to use just that to guess melt, basically. And when we do that, we get this picture. And so there's this bunch up in the left, and that's kind of to be expected. These are the cold shelves. So our parameterization is about the hot water intrusions into shelves. So if we think there's no hot water, we wouldn't expect to guess pretty well. But in these warmer shelves, some of them in West Antarctica, it seems like the parameterization does a really pretty good job, which is commendable based on how coarse the data we're using is. So yeah, that about wraps it up. The hub, we think, can be a useful metric for determining thermal forcing for points on the continental shelf of Antarctica for ice shelf models and parameterizations. And we think it can lead to hopefully better parameterizations and give new insights to cavities of all kinds. Yeah, thank you. And I'd like to acknowledge NASA and NSF for the early career travel support. Yeah.
Thank you so much, Garrett. Next we have Madeline Mamer with the effects of turbulent mixing on seawater intrusion, dynamics, and melting.
All right. Hello, everyone. My name's Maddie Mamer. I'm a third-year PhD student at Georgia Tech, where I work with Alex Roble. Today I'll be talking about some results on a project I've been working on for the last couple of years, thinking about seawater intrusion beyond the grounding line and what that means for dynamics and melt. So to orient everyone and to give a visual for what we are thinking of, this really nice diagram. So narrow in on the grounding zone. Traditionally, we think of this as a hydraulic barrier where we don't have fresh subglacial discharge interacting with salt water. However, some recent observations and modeling work has suggested otherwise. So my work kind of takes this approach of thinking what happens if we do have seawater intrusion beyond the grounding line, increasing the amount of ice susceptible to ocean-induced melt. Some of this previous work, this left figure, is from my advisor, Alex, where he looks at what if we include intrusion in an ISSM model and what that melt might look like. So all of those blue-green solid lines are an increase in melting if we include this intrusion. And then this right figure is just one of a number of observations looking at things like subglacial channels that cross the grounding zone and might provide a physical pathway for seawater to intrude and mix. So the way my work fits into this is asking two questions. The first one is, what does turbulent mixing mean for the ability for seawater to intrude? And then secondly, once we have this intrusion, what will the melt look like? And will this addition of melt change the dynamics of the intrusion? I do this by using a computational fluid dynamics solver. This is kind of an image of my domain. The ice is not actually there, it's just there to look pretty. This figure is showing a nice contour of density where the darker blue is gonna be our salty water and the light blue is gonna be our fresh water. We have fresh water coming in from this left side, your right side, and we have salty water coming in from the other side. The white arrows are my outflows. And this KE2 equation turbulence closer is how I'm modeling turbulence. It basically allows me to tune the degree of turbulent kinetic energy relative to dissipation. So I can kind of probe the model and tell it to do more turbulent mixing or less turbulent mixing. To show what one of my runs looks like, this is a fun little GIF. And so what we see is this salt water intruding past the grounding line, which is my white dashed line, and we see it mixing with that fresh subglacial discharge. Our first test is looking at if we tune this parameter C mu, if we increase or decrease turbulent mixing, how will that affect the ability for seawater to intrude? So here I have our three plots looking at three different magnitudes of freshwater discharge velocity, and the varying blue lines are going to be our varying degree of turbulence. And what you see, if you kind of note the x-axis, is the largest control is going to be our freshwater velocity. When we have high freshwater discharge at 5 centimeters per second, we're going to have much smaller intrusion because the ocean will have to act against much stronger velocities and forces of water. And then we see kind of the spread of turbulent mixing doesn't really have a large control. There might be a minimal trend, but really no significant influence. So this is pretty interesting because even if we have high degrees of turbulence, it won't inhibit the ability for seawater to intrude. The next steps, we're thinking about what does the change in geometry of the space mean for the ability for seawater to intrude. And I did this for only one of the freshwater cases, for kind of our middle case. What we see is it has a high dependence on geometry. So this orange line here is what happens if we decrease the slope of our channel, and we see an almost 10 times increase in seawater intrusion. And then this kind of pinker line shows what happens if we increase the thickness of the channel. What we see is about a 4 times increase in intrusion. So kind of conclusions for my first question is the main controls on the ability for seawater to intrude are going to be the geometry as well as the freshwater flux. Hopping into question 2, we now established that our our seawater can intrude past the grounding line. What does this mean for melting? Well, within my model, what I do is I add just a very simple function of near wall temperature, allow it to input some extra fresh water from this melting, and then run it all again. And I'm kind of looking at 2 things. I'm looking at what happens to the length of intrusion, and then I'm looking at what happens kind of dynamically within there. And so, looking again at this key figure, the red lines are going to be what happens when I include this extra source of fresh water from melt. And what we see is this melting actually kicks out the intrusion and inhibits the seawater from intruding further, in some cases by a large amount. Now, once we have this intrusion, what does this mean for melting? And I'm going to take a couple of minutes to kind of explain these figures since they're a little abstract. But this top left one is looking at the shear velocity. Shear velocity is really important for our melting parameterizations because a lot of our melt parameterizations are dependent on shear. And so this means that they're a function of freshwater velocity. What we have for our blue dots are going to be our kind of standard cases. So if we have no excess melt, and then our blue X's are going to be if we have that excess melt. And so what we see is when we include this extra source of meltwater coming in vertically down within the channel, we actually are going to reduce shear velocity, which is pretty interesting. And then the orange dot is just for the kind of retrograde sloping case, and we see that it follows a similar trend as well. So this increase in freshwater is going to reduce shear, which has potential implications for our melting parameterizations. And then this right figure is thinking of our middle and our slowest freshwater case, and it's the change in temperature on the top and the change in salt on the bottom between our melt-enabled cases, so the cases that have that melting function, and the cases that don't have that melting. So blue is going to indicate colder on the top row, and purple is going to indicate fresher on that bottom row. And what we see is that for our melt-enabled cases, we get colder and we get fresher water throughout our subglacial space. However, there's this kind of interesting thing where my head's currently at is near the top, so you can think of the ice being at that 0.05 meter mark. Near the top, we actually get a little warmer pocket of water when we have melting turned on. And so kind of thinking about how the dynamics of this increased melt coming from the top may be pushing the wedge, the seawater intrusion to be taller, or maybe enabling more vertical mixing, might be able to deliver warmer water up to the ice near kind of the start of the channel. Kind of the last takeaway from this project is thinking about how our current parameterizations handle such melt dynamics and such seawater intrusion. So the red line here is going to be my modeled melt. It's coming out of that equation. The blue line is going to be the melt that would happen if we had no freshwater flux from melting. So if we allow the seawater to intrude to its full potential. And then very small towards the bottom, I have this orange and green line, which is our parameterizations. And so what we see is a couple of things. A, including this excess buoyancy flux from melting will reduce the ability for the intrusion to cause melt. That's the difference between the red and the blue line. And B, that our current parameterizations don't do a super great job of estimating this melt, at least on a kind of a first order approach. Both a diffusive parameterization and our classic 3-equation Jenkins parameterization don't emulate kind of my modeled melt very well. So thinking about key takeaways and answering this question 2 of melt dynamics, we're seeing that this additional buoyancy forcing will decrease the intrusion distance, will change the fluid dynamics of the channel, and is not estimated well by current parameterizations. So moving forward, thinking about how we can include such thing in coupled ocean models, we need to kind of rework how we define the grounding zone, how we extend our ocean force melt beyond it, and how we model this melt as well. Thank you.
Thanks for that. We're going to step into the atmosphere for a moment with Emma Robertson, who's going to talk about atmospheric rivers and how they show up in the ice record. I'm going to find your talk for you. That's yours if you need it.
Thank you. Hi, everyone. My name is Emma Robertson. I am currently a student at Penn State, but I'm soon to be at AVI. And I'm going to be talking to you today about looking for atmospheric river signatures in Western Arctic ice core records. So we've done a little bit of an overview earlier with Michelle on atmospheric rivers, but they're pretty important for the Antarctic ice sheet, particularly for this Western Arctic region. They're pretty important in terms of modulating interannual variability of snowfall, and atmospheric rivers in terms of just the broader spectrum of extreme precipitation events might be linked to part of what this work was thinking was that this long-range moisture transport might be visible in the ice core record isotopically. So a little bit of background on what an atmospheric river is. There are these long, narrow bands of moisture transport. And in Antarctica, they're the predominant mechanism of poleward moisture transport. If you're from the West Coast like myself, or you've been there recently, especially earlier this year, you definitely experienced some of the power and precipitation from atmospheric rivers. So some of the questions that I looked at through this work was, what's the relationship between atmospheric rivers and delta 18? And also, what kind of synoptic environments influence AR and delta 18 relationships in Western Antarctica. Some of those synoptic relationships that I looked at were ENSO, the ASL, so the Amundsen Sea Low. I'll focus in particular on the Amundsen Sea Low today. So a little bit about these core sites in Western Antarctica. They're at Pine Island, Thwaites, and at the Drainage Divide. They were collected in 2010. They date back at the earliest to 1786. But for the purposes of this study, I looked at the overlap between NASA's Merit 2 reanalysis data sets and the core record, so starting at 1980 and up to 2010. We created a composite delta 18 record of these cores for spatial analysis and comparison of looking at different atmospheric modes. Wanted to get a little bit into the weeds of how we classify or track atmospheric rivers. So we do that through integrated vapor transport as one method. For Antarctic atmospheric rivers, we use particularly the meridional component, so that V in the VIVT. In there, you can see some of the components that we use to calculate VIVT. For this study, I used Jonathan Willey's air detection tool from the 2021 paper to mask outputs from Merit 2 in terms of precipitation and integrated vapor transport. So in this first draft, we looked at the record of all record, Merit 2, VIVT, and the correlation between Merit 2 VIVT. And what we can see here is that it seems like there's a pretty clear link between polar moisture transport and enrichment of delta 18 in these cores, which would point to a pretty broad trend, which would point to a trend in terms of polar moisture transport into this Amundsen embayment that enriches the delta 18 record in ice cores. Here on the right, this is VIVT, so that polar moisture transport, but just looking at what we've classified as being related to atmospheric rivers. Another thing about classifying VIVT and precipitation from atmospheric rivers, we classify them during the atmospheric river event and also 24 hours after. We find that the effects of atmospheric rivers in terms of precipitation and that moisture transport tend to linger, so we include during the event and also 24 hours after. what you see here, at least over the Antarctic Peninsula, is a pretty broad blocking pattern that we typically see during atmospheric river events, which directs moisture transport towards that Amundsen Sea embayment. Some of what I also looked at as far as drivers of this isotopic composition was the Amundsen Sea low. Previous work has shown that the Amundsen Sea low is pretty important for modulating the frequency and also where atmospheric rivers landfall in West Antarctica. So yeah, the Amundsen Sea low can influence the formation and intensity of atmospheric rivers in the Amundsen Sea sector. And also high snowfall, what's also been found is that high snowfall is associated with a low central pressure and also when the ASL is located west of the region. So what we see with this, at least from looking at the composite record from these ice cores, is that when the ASL is more east, so generating more northerly outflow from WAIS, there's lower values of VIVT and depletion of delta 18. So this is a pretty quick talk. I got pretty nervous, so I went pretty fast. But the main takeaways is that we see a pretty significant association between area VIVT and isotopic enrichment, which we think likely owes to the lower latitude origin of atmospheric river moisture. But then again, disentangling those effects of atmospheric rivers versus the synoptic state variability of isotopic records remains challenging. Another thing also is that in this moisture transport, you're not just seeing atmospheric rivers, you're possibly, in the broader moisture transport, you're also seeing moisture transport from other extreme precipitation events that we haven't classified as atmospheric rivers. So overall, further investigation needs to fully understand the impact of atmospheric rivers on the isotopic composition of atmospheric rivers, of ice cores. So, yeah.
Thank you, Emma. Next we have Peter Washam with Ice on the Move, what observing the underside of Antarctica's ice shelves now can tell us about future sea level rise. Oh, sorry.
Good morning. It's been great so far, all the talks. I'll try to keep up. So I'm going to talk a little bit about what we've been doing with IceFin, kind of as more of a summary, and hopefully a look to sort of the future of how we can use IceFin to improve larger scale models. And in case you don't know, this little yellow pencil thing is IceFin. It's an underwater robot. It can go through really narrow boreholes. And all of this work has been done with a long list of collaborators. It's too long to put on the slide, so if you want to know, I can tell you. Okay, so this is where I could trip up for the first time. All right, so we know that the ocean is important to forcing the ice sheet, right? And it responds to different perturbations. So this is a really cool video from NASA, and that's Thwaites and Pine Island, and then over here is Cam Ice Stream, and that is not flowing, and Thwaites and Pine Island are flowing really fast. So I'm going to show some data comparing those two locations and kind of showing what we're seeing from IceFin. This I can kind of just skip through. There's a lot of ice in Antarctica and Greenland, can raise the ocean by a lot. But what's interesting is the projections by 2100 are huge, right? There's huge ranges. For Antarctica, this paper is citing something between 6 and 53 centimeters of sea level rise, and Greenland is 2 to 25. So these ranges, it's just too much uncertainty, right? So we're trying to improve that, all of us in this room, in our own different ways. So my favorite glacier in the world is Petermann Glacier, and I'm going to show you just a little example of how it responds in different climate warming scenarios. Another great promotion for NASA and I think this is on their YouTube. But you see how it's responding under low, medium, and high forcing, and just how much more it retreats. Slight complaint for both of these, there's not a scale bar or a color bar on either one of those videos, so it could be improved a little bit, but still great. So yeah, the ice ocean boundary layer, here's a schematic from this paper right here. It's basically what we're looking at is in different scenarios how the ice ocean boundary layer looks, and sort of a neutral stability, and then as you start melting the ice, this is now in this example sea ice, but it's all the same for an ice shelf. As you start increasing melting, you start to stabilize this layer near the ice, and then instead when you're freezing, you're destabilizing it. And then on a vertical wall, you have a different scenario here, which I'm not going to talk a ton about, but it is there for you all to look at. So really close to the ice, you have molecular diffusion dominating a lot of stuff. Go talk to Ken Zhao about this if you want. And then further away from the ice, you have turbulent mixing. I'm just going to talk about shear-driven turbulence here, guys, so don't come at me with any of this other stuff. But you can sort of calculate with observations these different transfer velocities in this scenario for temperature and salinity. And these, all the yellow stars are turbulent parameters, and all the blue stars are molecular parameters. So both turbulence and molecular diffusion is important. Most of the time with observations, you can't get to this level of detail. We're lucky enough in one example to get to that level of detail. So more typical are these sort of parameters that we all get tired of hearing about, gammas and CDs and whatnot. But they're important, and they're simple. You can stick them in models and run them forward. And typically what happens is there's just these set values from a paper in 2010 from Adrian Jenkins and company they're just used as the ground truth, which is not the case. In different ocean settings, you have different levels of stratification, and those values for these are called Stanton numbers, cannot be used unanimously. You will be very wrong in your projections. So here's just two examples that I'm going to talk about. One is Thwaites, so Icefin's big debut, and then the other one's over here on the Ross at the Cam Ice Stream grounding line. Thwaites is warm, it's moving fast. The ocean where we were right next to the ice base was about 2 degrees above freezing, and over on the Ross it was very cold. It's close to freezing. And the ice there is stagnant, actually, and it's not just because the ocean that the ice is stagnant. There's plenty of dynamics. I'm not saying that upstream of the grounding line that are feeding into that, but certainly as just a first order forcing, we can compare these two sort of end members for Antarctica. So here are some data from Icefin in 2 crevasses. One at Thwaites, which is this one, and then one at Ross. Interestingly enough, these crevasses are about the same size. So they're each about 50 meters tall vertically, but horizontally, you can see the Thwaites one is just so much wider, right? It's like 3 times the width. So this is sort of bragging on all the stuff Icefin can do, right? So here we have the tracks of Icefin colored by thermal driving in each of these scenarios. And then all these little messy points underneath it are the velocity into the page or out of the page collected with Icefin's ADCP. And these data, I think, are really incredible. I'll take a moment after I get through this to just sort of show them. And then finally, there's 2 different ways that we've sort of parameterized the melt in these regions. Obviously, there's no data up here. So what we did was first there was 3 AP res laid out, and this is all outlined in the Schmidt paper, but Schmidt et al. 2023. But basically, we binned the regional sort of TS and U and varied our gammas based on the slope of the ice, and they were constrained by an AP res, which showed, or 3 AP res, which showed the flat ice was melting quite low, despite there being plenty of heat in the water column. So it was melting at something like 2 to 5 meters a year, but the steep ice was melting at 70 meters a year. So the best we could do with this sort of first order approach was get at 30 meters a year, just by simply varying based on the sign of the ice base angle these heat and salt transfer coefficients based on publications from observations. So getting through all these details as quickly as possible. These are the 2 papers, that Jenkins one, and then there's this one from 2020. And basically, low gammas equals stratification reducing melt. High gammas equals no stratification really influencing melt whatsoever. Now, on the Ross ice shelf, you have melt rates here varying between minus 0.2 and 0.2 meters a year. So 2 orders of magnitude lower than the highest. And you actually have freezing. And these data were good enough to actually, I basically binned these profiles of TNS, and then I took these different, and then I took profiles of the currents, and I could directly calculate the friction velocity U star in different parts of the crevasse, which actually interestingly had different morphologies on the wall. And then I could calculate these transfer velocities and then boom, get the stuff that everyone wants to stick in the model directly. So this is in press. Hopefully it comes out next month or so in Science Advances, but it's sort of another step forward in this story. So just to brag on these data a little more, unfortunately it's a little fuzzy on here. This is the sort of stuff that we were able to collect in this crevasse. So you have 3D velocities. So you have V, which is into and out of the page, U, which is across, and then W, which is vertical, rising and sinking. So there's an overturning. So this stuff is like a downwelling plume, which is really nice. And then all the data near the walls was thermal driving, salinity, buoyancy frequency. And then these are images of the crevasse walls at different parts, and they're all scaled. So you have scallops with different scales, you have marine ice, you have these cool runnels, which actually go the whole length of this wall, and they get down to like 2.5 meters deep and 5 meters wide. I have to go. All right, what's next? We're gonna do this for Thwaites. Here's a little video. And Brittany and co are going to Fimble Ice Shelf next 2 months from now, which is sort of the in-between region. And I've started to talk with modelers, but I think we should talk some more.
Thank you, Peter. We have a take into the and high experiences changes, and we have Paul Summers, whose presentation I'm going to look for while you make yourself comfortable. How do I make it big?
That's a good question.
Ooh, maybe that's going to be good.
Maybe. I think so.
Yes.
Right.
Okay.
Well, thanks.
This is for you if you would like it.
Thank you. Thank you. Yes, I'm Paul Summers. I'm a 6th-year PhD student at Stanford, and I'm going to be talking about our work at Conway Ice Rise. And I'll try and get this little thing to go away. I'm not always in Adobe. This is my first time doing the PDF version of a slideshow, so we'll see how it goes. But first, I'd like to thank all of my collaborators. They spent years of their life collecting, processing, and analyzing all this data, and it's been really fun to come in and get to work with them on this data model integration. So zooming right into our field site, build some context because we only have 10 minutes. But we're looking at Conway Ice Rise. This is on the Saiple Coast. And it's a relatively well-studied area of Western Antarctica. A number of modeling studies have been done here because it's a nice natural laboratory to study ice streams and ice rises. And then also there's been a lot of geophysical study there, looking at the history that's ingrained in the radar layers there, indicating both regions of long-term stability, as well as some regions of rather recent and very large-scale rearrangement of ice flow, namely the Cam ice stream. And so we think this is a great place for us to bring together modeling and observations to try and probe the history of Conway Ice Rise, which we'll see might be a little more complicated than other ice rises. So now taking that map, which is ice speed velocity, or ice surface velocity, and now we put on top gray contours. These are contours of topography. And we can see how Conway looks quite different from its friend Engelhart on the other side of the ice stream, in that it lacks a central topographic divide. And this is seen as an indicator of less long-term stability of the ice rise, Conway ice rise that is. And then additionally, radar observations of the layers tell a similar story, that there's been a complicated past of flow rearrangement on Conway ice rise. And then finally, there also are observed height changes and flow speed changes that are observable from satellite data products above the noise floor there. So that's an indication of sort of current day rearrangement as well. And so going all the way back to sort of the larger project, this was started with a bunch of fieldwork back in the early 2000s, where they collected a number of mass balance stakes and velocity stakes, and over 300 kilometers of radar surveys, which is what we'll be going through some of today. And in the larger work, we break the ice rise into 4 main components, which I don't trust myself to figure out the pointer, but is a small orange area near the tip in the lower right as you view it, a green area, a blue area, and then a kind of hard to pick out, but a purple area. And in the overall work, we gauge the stability of all of these regions, but today we'll just be focusing on the promontory in that lower right in orange. So zooming in there, the promontory is sort of placed right between the Mercer and Willans ice streams. And we zoom in on this one radar line that's in black on the map that we see, and the blue dot, which is at the tip of the promontory, then moving towards the center of the ice rise, we see in the radargram C over on the right there. I thought I'd be able to physically point, but I hope you can see it all. And on that radargram, we interpret some crevasses and disrupted layers as we're moving left to right across the radargram, which we interpret as historic rapid flow across this region of the ice rise that now is locked. And then above that blue line, which is the time horizon where this transition occurred, we see continuous layers in support of the sort of stagnant ice we observe today. And then on the far right of that radargram, we see continuous layers all the way through. And so this gives us an estimation of where that historic shear margin likely was, where we transitioned from stagnant flow to rapid flow. And so that leads us to our model setting, sort of say, okay, we have a radar observation where we think we've seen this historic shear margin migration, but how can we use a model and put in other data sets that we're aware of to support this conclusion that we find in the radar data set? And so to build up that model, we draw our nice little red domain around. We use surface and bed elevations for the present day from bed machine, and then we feed in a historic surface based on the currently observed changing in surface heights today. We kind of run the clock backwards on surface elevation, and then here we're using bed strengths from an ISSM inversion. And then really quickly running through the model, we solve for a 2D depth integrated force balance. And the big key here is that we're using a free boundary model. And so this model is solving not only for the velocity of the ice everywhere in the domain, but is also solving for the locations where the ice goes from being locked to the bed, transitioning to a sliding ice stream. And that is the location of our shear margin. And so this design of the model is specifically targeted for us to look at a moving shear margin and how it might have be coupled with the historic driving forces to reproduce our radar observations, or to confirm our radar observations. And so one last connection, which brings us to the oceans, is that when we look at the whole ice rise, and particularly the promontory on the lower right here again, we see that it's very close to flotation. So this region in present day is only about 100 meters above flotation. And so we had 2 hypotheses that we really wanted to look at here and to see how well connected that bed was to the ocean nearby. And so we have 2 cases of basal strength, one that is constant in response to thinning. So no matter how much we thin, we always say that the bed strength is going to be exactly the same. And then the second case, we're going to vary that bed strength with height above flotation, sort of which can be a transition as we start to approach flotation, but the bed strength will get proportionally weaker as that effective stress at the bed is proportional to the sort of effective overburden of the height that's above flotation there. And so jumping right into our modeling results, first I'll show you our height above flotation model runs. So in the upper right of this sort of grid of 4 is our modern, present-day, no thinning applied model run. And we can see there's ice velocities there in bright greens is fast, blue is slow. There's a thin dotted line that is the shear margin. And we can see that that case does get the shape of the ice rise fairly accurately today, including a locked promontory. And then when we move to the thinning case, which is the sort of upper left of this 4, we've applied about 20 meters of historical thinning. And in that case, we see rapid sliding across the promontory in a shear margin location that's fairly consistent with the radar-derived estimates of the shear margin. And then the lower left of this quadrant is the change in speed, where the reds indicate that there was historically faster flow. And then in the bottom right, that's the actual surface height change that we've applied between these two cases to then sort of our inferred historic ice surface. And then that is in comparison to our no height above flotation run, where we kept the basal strength exactly the same. And in this case, our present day model run is the same, but shown again for reference. And then our historic run here has a much more stable shear margin, and we see that the promontory is still locked in that region. And so from this modeling, we conclude that our radar observations are most compatible with this bed strength that is dependent on height above flotation for this region. And one extension that we're really excited to work on is to try and resolve where stresses are great enough in our modeling runs to produce surface crevasses, and then see if those crevasses line up with our buried crevasses that we can see in the radar data sets as well. So it's trying to draw as many connections to observables in the radar data sets as we can. So in conclusion, I hope you believe our interpretation that the promontory experienced rapid flow in the recent past, and that this scenario is most well supported by bed strength that's varying with height above flotation, suggesting a strong connection to the ocean in that region. And then the larger takeaway, I'd like to inspire everyone to get more excited about data model integrations. I think they're great. I think everyone should love them. And this is a nice example of how we can use the two together in the interpretation stage to learn more about past conditions and the processes that connect present day to the past. And thank you very much.
Thanks, Paul. Next, we have Ruth Moorman with coastal plinias enable transitions between high and low West Antarctic ice shelf melt rates.
Okay, great. I'm going to try and figure this out first. Maybe? Oh, okay. So hello, my name is Ruth. I'm a PhD student in physical oceanography at Caltech, and today I'm going to be talking about some idealized modeling work that I've done looking into potential drivers of warm water thickness variability right up near ice shelves in the Amundsen Sea, and particularly at the Dotson ice shelf. First of all, I want to acknowledge I've done this work as part of my PhD with Andy Thompson at Caltech, also working with Earl Wilson, and that it's been funded by the General Sir John Monash Foundation, and I also want to thank the travel support of the WAIS Workshop. Okay, so I want to start off by situating us in the Amundsen Sea embayment of West Antarctica here. As most of you will know, the Amundsen Sea hosts a number of rapidly melting ice shelves, including, I'm not going to use the the pointer in the end, including Thwaites, Pine Island, Dotson, and Crossan, with rapid ice shelf melt observed here associated with warm waters called modified circumpolar deep waters. So on the right here, since I know that we have a lot of people in the room who are not oceanographers, I've got a little example profile of a temperature profile we might expect in the West Antarctic Ocean region, where essentially you've got a layer of warm water that's actually salty, so it's sitting at the base of the water column, which is our modified circumpolar deep water. And then that warm water is separated by a thermocline with winter waters, which are cooler, fresher waters associated with sea ice processes from preceding winters. So if we keep this kind of schematic in mind, and we go to some observations that have been taken from the ice front, some hydrographic or ocean observations that have been taken from the ice front of Dotson ice shelf, we can see that there have been a cluster of years, 2006 to 2011, where there has been a consistently really thick layer of warm water at this Dotson ice front region, followed by a cluster of years, 2012 to 2016, where we've had a relatively thin layer or a deep thermocline. And the depth of this ice front thermocline has been varying by large amounts, as you can see in this picture, 300 to 400 meters. These big fluctuations overwhelm longer-term trends in the region. As I should say at this stage, I'm going to be showing mostly work that is focused on the Dotson ice shelf, but a lot of the concepts that I'm going to be presenting and the model that I'll be talking about is applicable to other West Antarctic ice shelves that are adjacent to latent coastal polynya, which I'll get into more later. So because this variation in the thickness of the warm water layer is so large and has been linked to changes in basal melt rates in the area, there's been a fair amount of work trying to figure out what drives this thermocline depth variability in front of the Dotson ice shelf. And that's been split into two main categories, one which has received a lot more attention than the other. The first being that winds drive variable amounts of warm circumpolar deep water from the off-shelf region onto the coast. Through various different mechanisms, but the basic idea being that there's more warm water transport towards the coast, the volume of warm water transport converges, and that thickens that warm water layer at the coast. So I like to think of this as supply variability. The amount of warm water brought to the region or supplied to the region is changing. The other kind of category of forcing that you can think about is latent heat coastal polynyas in the area. So if you're unfamiliar, latent heat coastal polynyas are areas where strong katabatic winds are pushing ice away from the pushing sea ice, I should say, away from the ice front and allowing there to essentially be this like conveyor belt system where sea ice is pushed away, exposing ocean water to the cold atmosphere. More sea ice can form, it gets pushed away, and so on and so forth. So the continuous production of lots of sea ice that can lead to large buoyancy exchanges between the atmosphere and the ocean, making the surface waters denser, and that can have a really important influence on vertical mixing. Essentially, you can have convection in the water column in the winter, and that can erode this warm water layer at depth and make it thinner by diverting heat from the deep warm water layer into the atmosphere. So I think of that as sort of demand-side variability. Right at the coast, there's changes in the amount of heat that's being diverted away from the ice shelf cavity, away from the direction where it could go into the ice shelf cavity and into the atmosphere. So the aim of this project was to develop a really simple model that we could use to compare the effect of these two forcings, the variable supply of warm water and the variable consumption of warm water due to vertical mixing in these polynyas. The simplicity of the model was like a really big focus of this project because we wanted to be able to clearly target the question, can reasonable variations in warm water supply and surface sea ice formation cause such large changes in the thermocline displacement that we're seeing in the observations? We hadn't really had a lot of like quantitative calculations to say if you have this amount of extra warm water coming towards the coast, can that actually inflate the thickness at the coast by the amount that we're seeing? By as about 300. So formulation, the equations and whatnot, given the shortness of this talk, but this work is published so you can have a look at it. I'm also happy to go through it with you later. So instead I'll talk kind of about the sort of general, I guess the model ideology you could think of, which is a overturning model, an ice front overturning circulation model, and it's a really simple box model. So the important concept that we're thinking about is we're saying that if there is a net transport of warm water towards the front of the ice shelf and a net transport of cold fresh water away from the front of the ice shelf, i.e. like a net exchange or an overturning circulation, then that overturning circulation needs to be closed by some form of transformation of the warm waters into the cold waters. And we're saying that that transformation can occur by two main pathways once you get right up close to the ice shelf itself, that being the main one that people think about, which is that the warm water is driving melt within the ice shelf cavity, mixing with buoyant melt waters, and then turning into lighter waters and entering the thermocline. But the other being that in front of this, in the area right in front of the ice shelf where we have this latent heat polynya, you can have enhanced mixing that can directly, through vertical mixing, transform these warm circumpolar deep waters into the cooler thermocline waters. So that's the basic premise. The model is then forced by two parameters. The psi-in term, so the amount of warm water coming to the ice shelf, is an externally forced parameter. And the other externally forced parameter is the surface buoyancy forcing, so this F-surf term here. So we change those around to see how the thermocline depth can vary in response of those two nicely, cleanly separated forcings. So onto some results. I'll start with some results that we have from the steady state solutions of the simple model, and then I'll move on to some time evolving solutions very quickly at the end. But the main results from the steady state solutions of the model is that the model supports two steady states for a given set of forcings, one with a thick warm water layer and one with a thin warm water layer. So that means that for the same amount of warm water supply from the open ocean to the ice shelf front, depending, as it turns out, on the convective conditions, the vertical mixing conditions, you can end up with as much as, I said, as you see in the observations, about 300 or 400 meter differences in the thermocline position at the ice front. And so this is a bistability, essentially, two stable states for one set of forcings. And it's supported by a fairly intuitive feedback, which is basically when you're in a high melt condition or a thick warm water layer condition, that's driving more melt in the ice shelf cavity. That adds more buoyancy to the surface layer of the ocean in front of the ice shelf cavity, and that presents an extra resistance to vertical mixing as forced by the coastal polynya. Essentially, your coastal polynya will have to work a lot harder to get rid of that buoyancy before it's able to drive convection. So it's a self-reinforcing state. And in basically the opposite in the other case, that if there's a small amount of warm water at the ice shelf front, it's not going to add a lot more buoyancy. The melt that it drives in the ice shelf cavity won't add that much more buoyancy. And so the water column will be preconditioned for convection in the wintertime, and you'll be able to sort of sustain that low melt state. This should be said to be, with the model forced by values of those forcing parameters that we've gotten from regional ocean models, because there isn't like particularly good ways to get this from observations at the moment. So then the question is, can this feedback explain the observed variability? So I'll go back to the observations for a moment. So if we take these profiles of temperature that I showed at the start, if you then from those get a metric for the depth of the thermocline and also a metric for the strength of the stratification in the whole water column, you can see that in the years with, we've got stratification strength in circles here and the thermocline depth in the crosses, and we can see that when we have a shallow thermocline or a thick warm water layer, we have a strongly stratified system, and then when we have a deep thermocline or a thin warm water layer, we have a weakly stratified system. And then really nicely and importantly in the middle here, when we transition from the warm state to the cool state, we actually see that the stratification changes first before the thermocline changes. And at the end there, I don't have to have the observations past 2018, but we actually see a transition in the other direction where we see the thermocline change before the stratification changes. And I'm out of time, but I can basically say that when we force our model with temporally varying forcings and seasonal perturbations of those forcings in particular, we can basically reproduce that pattern of variability, and in particular that phasing of variability, irrespective of what we're perturbing the model with, which leads me to my main takeaway, which is that the feedback between basal melt and the ice front convection may be much more central to the variability that we see in this region, as opposed to changes in actually either forcing. Either forcing could drive the change and it would look the same. It's much more related to the feedback. And I'll leave it there.
Thank you very much. I see the hope for connections coming together. And now the last presentation for this session is Jamin Greenbaum, whose talk I will now look for. who's going to be making observations of those waters off Thwaites. Yes, this is for you. That is the pointer.
Good morning. So thanks for the organizers for putting my talk where it is. It's perfect. So appreciate that, all the hard work. I'm motivating this presentation by this map, which shows the Smith et al. 2020 ice surface lowering data set from ISAT. Just to highlight, in offshore, you see bed machine, excuse me. And then the black lines show where ships have sailed. And so this is just your daily reminder that we have not explored the continental shelf adequately, especially near regions of thinning ice. So this talk focuses on Thwaites Glacier, some data that we collected in early 2022. But really this represents an idea for thinking creatively about how to get to this environment and collect some of the data that we need. So as I said, we're focusing on Thwaites in this talk, but in East Antarctica, we're collaborating with the Australian and French programs using Basler surveys and there we go, that's weird. And also the Japanese Antarctic program using their icebreaker and helicopters to survey the Sabrina Coast area. So this work was just published this year by Daisuke Hirano and Yoshihiro Nakayama, some papers that just came out. So in a lot of ways, what the talk that I'm giving is an extension of that work and sort of taking it to the next level in complexity, as you'll see. The work is sponsored by two NSF, I don't know what happened to my cursor. Two NSF projects you see down here, and a NASA cryo project here, as well as a few other sponsors. So motivating the work, like a lot of the talks we've seen, is trying to understand why basal melt rates are so high and higher than our predictions say they should be with the observations that we've had available. So this is also a plug on the left to Tyler Pelly's talk on Thursday, where he is going to be presenting a modified version of his PCOP parameterization that includes the effect of subglacial discharge. But this map on the left shows Tyler's parameterization without subglacial discharge. The panel in the middle shows Sushil Adusumili's basal melt rate for Thwaites, published in 2020. And then the panel on the right shows the difference between the two, and then the colors on the grounded side of the grounding line show Christine Dow's predicted subglacial freshwater flux. So you see that big anomaly in melt rate corresponds to where most of that subglacial freshwater is predicted to cross the grounding line. So the idea for this project, now I should say that those parameterizations are obviously dependent on the temperature and salinity in the cavity, which we haven't traditionally had access to before the ice fin revolution, as you saw in Peter's talk. But Thwaites, because it collapsed between 2012 and 2016 in the the western side, the Thwaites Glacier tongue, we have this unique opportunity to acquire depth profiles potentially in that rifted tongue. So the sensors that we use are nothing new. They are called expendable CTDs and expendable bathythermographs. Some details here, but I just wanted to highlight on the left how normally when you deploy these things, they go into the water, they go under the water, the case falls away, a little surface buoy goes to the surface and begins transmitting a VHF signal to the aircraft while a sensor descends through the water column. So I'm highlighting that because that became a problem in this project. The Oceans Melting Greenlands project, shown here, this is an AXCTD coming out of the Gulfstream aircraft. And then the work that the Japanese Antarctic program did on the bottom right show what a normal deployment, where you can just throw the probe out and a parachute opens and it falls into a target. So in early 2022, when I deployed to Antarctica with the Korea Polar Research Institute, the sea ice conditions were really bad, and that was partially because of this iceberg B-22 that was sort of in the way, and so we failed to get to Thwaites. You can see the the black circles show us the closest approach. So fortunately, I mean, you can imagine we were all very disappointed in this. But fortunately, the Copri team sails with helicopters. And so that didn't stop them from acquiring aerogeophysics upstream and downstream of the grounding line, and then also tagging seals all around Thwaites. So it's important to acknowledge, though, that this required flying over 100 kilometers. This is about 130 kilometers from the closest position of the ship just to even get to Thwaites. So we had to set up fuel caches upstream of the grounding line in these two places. So these flight lines show just the lines from the AXCTD flights that I'm here to talk about. But the helicopter was deploying AP-reses, the tagging seals, doing the aerogeophysics. I mean, it was just annoying because of the transit time, but the science could proceed. In the end, we acquired 10 successful AXCTD profiles in this area that you see here. And then the colored dots, the other colored dots, we'll come back to in a moment. This is what those profile locations look like in the context of a Landsat image from almost the same day that we acquired the probe, the sensor profiles. And then the overlay shows Sushil's basal melt rate data set that I mentioned before. And so you can see, this one in particular is really exciting because it sampled an area where Sushil said the melt rate should be up to 80 meters per year. So in this red box, it was like the old method. You just throw the probe out and the parachute opens. In this case, I'm going to skip through this, but basically the environment down there was really weird, and we were really surprised to find open water in this location because the ice around here should be like 700-800 meters thick. So what it required was basically taking apart the sensor, improvising in a short period of time to remove the sensor and then make what we called Shackleton bombs, because we put mooring shackles in these tubes, made a hole in the ice, and then put the AXCTD sensor on custom spools that we lowered into the hole that we created with the Shackleton bomb. Once the sensor is in the water, we just told the helicopter pilot to go ahead and fly away so that the rope stays behind and doesn't become a potential safety problem with the helicopter. So at this point, the pilot is ascending, paying out the rope, and the sensor has started communicating with the aircraft. So with my remaining 2.5 minutes, what does the data look like? So profile A to A prime and B to B prime are shown on the right. And the big takeaway is that there seems to be warmer water in the upper 1 to 350 meters or so of the water column as you get closer to Thwaites. Comparing the profiles to all the previous data around Thwaites, which these are the colored dots I mentioned before. So in each of these panels, profiles 1 through 4 all look pretty similar to what you find elsewhere in the Amundsen Sea, although you do get these dark red areas, which means that our profiles were warmer in those deeper layers than any of the previous average profiles, at least in this case. But then you get to profile 5, which was that really wild one that I highlighted before, and you get this ridiculous warming that I mentioned, and you see that in some of these other profiles as well. So in this case, the deep red is where our new profiles are warmer than any of the other profiles collected before, and then the less red is where it's warmer than at least one of the other average profiles. In blue, obviously, it's cooler than the other ones. So we tried estimating meltwater fraction, and if you're thinking, well, wait a minute, those sensors don't have meltwater, don't have dissolved oxygen, you're right. So what we had a little bit of reading, used a member from the cast 30 kilometers away, right? So not great. But if you take that approach, what you see is that profiles 1 through 4 are all basically the same. Then these profiles closer to the inside the Thwaites Glacier tongue all plot along the meltwater mixing line, and you get these higher concentrations of estimated meltwater in the shallower layers. So I'm almost out of time. I just want to quickly say that we've computed relative heat content and also this kinetic energy dissipation rate. And there's an interesting relationship here that I'd love to talk to anybody about that's interested. My remaining 30 seconds. And I just want to come back to that idea of subglacial discharge. So we learned from Peter Davis's paper, and others, by the way, but I really like Peter's plot here, that subglacial discharge should show up kind of like this. should plot parallel to this end member line. And so it's not obvious in our profiles that that's happening, but it's not obvious that it's not happening either, right? There's this interesting behavior in these around 0 Celsius in these circled areas that might sort of be subglacial discharge. A more indirect way to look at this is using Adrian Jenkins' 2011 plume model. Tyler Pelly did this here. Basically, the best fit to Sushil's data along AA prime is if you use the AXCTD data to constrain the cavity temperature and salinity and use that subglacial discharge. And I'll stop there. Thank you.
That was great. If I could invite all of the speakers from this session to come and take some to not leave, and to return and take seats along here. And while they're gathering, go ahead and clap for them all again. Thank you. What I really want is this. To quickly remind you, I think everybody with an asterisk is a student. Oh yeah, thanks. And you can use that QR code if you want to give people feedback on their presentations. But better than that, we now have the opportunity to have a discussion with all the speakers together, pull together all of these brains who have been measuring the ocean, modeling the ocean, thinking about the calving front, thinking about the grounding line, thinking about the ice, thinking about the atmosphere. There's been a lot. You have questions. You have questions for each other. And since you guys are all closest to a mic, apart from me, do feel free to talk amongst yourselves in these discussions. There are people online, and we know you're there, and we welcome you to contribute your questions if you would like. We are checking online. Your voice won't be heard, but your thoughts will be. And anybody in the crowd who wants to ask a question, it would be great to come up to the mic here. If there's a reason you don't want to do that, wave your arm around and we will send a mic to you. Anything else that I needed to say to start this discussion? This is going to be fun. Could we have a question, please?
Great talks, everyone. Kind of a survey question for everyone up there. If you're a modeler, what observations or data, and if you're an observationalist or have worked with data, what models, be as specific as you can, would really guide the next steps or kind of big picture how your work can, evolve or expand as the next step that would be most useful to you. Thanks.
Or one of you grabs the mic and then hands it down the line, because everybody can have a turn at this.
Yes, I guess as more of a ice sheet modeler, I think for me, the big question would be any observations we can get of subglacial hydrology, anywhere from at the grounding line to all the way inland, would be super valuable to incorporate into models. And so it's really neat to see, especially some of the meltwater intrusion work, to see how that can be integrated at the grounding line, where it's very important as well.
Okay, I would say for me, a really big one is sub-ice shelf bathymetry, having some better estimates of sub-ice shelf bathymetry, and I know that there's some poster work going on that you can have a look at later today about that, which is great. Another one, which is not so much glaciologist work, but I know some people work with, for example, ISAT, and may have thoughts about this, would be long-term estimates of the variability of sea ice formation rates in latent heat polynyas that we could then use to estimate changes in buoyancy forcing near the coast of Antarctica. And then, of course, as always, just regular profiles near the coast would be fantastic. That's more for the oceanographers, but yeah.
Yeah, I guess I'm just excited for Bed Machine 3.
For myself, on the observational side, I think it would be interesting to have isotopic measurements from snowfall during atmospheric river events. On more of the modeling side, I've been looking at using the isotope-enabled CSM, but also some moisture source and looking at back trajectories during atmospheric river and also other extreme precipitation events.
I think from the modeling, I think the things I'm excited to see or I want to see more of is starting to get into more of this ice slope stuff with the melting, and then starting to use a gridded drag coefficient and transfer coefficients on an ice shelf. So like a coupled ice sheet ocean model, which has been done, but you just slide the drag and the gammas at different places on that ice shelf to see not only the melt map, but also the result on the upstream ice flow.
Two things that come to mind at the moment. One, I think it's really important to highlight the Polar Geospatial Center and the digital elevation models that they're making. You know, I didn't have a chance, couldn't include it in this talk, but we're looking at some basal melt rates derived from the 2-meter products that Mike Cloquet and Diego Osorio have been making for us. And we've been comparing those melt rates to AP-Res. And for Thwaites, it's super complex, and so you need that high resolution from those Maxar images. And the estimates of melt rate we're getting are actually lining up pretty well with the AP-Res data. So I mean, that's like really exciting and potentially transformative, and so, well, certainly transformative. So I just want to say like more of that. That's great, please. And then beyond, what's that? Oh, hey, there you are. Wow. Yeah, nice to meet you. And then I also want to say geothermal heat flux. I just want to sort of start that in the discussion. I think we need to do more work there. And yeah, I'll stop there.
I think the first thing that comes to mind for observations is just increasing the temporal range, specifically for the intrusion problem, for thinking of it on tidal timescales or seasonal timescales. So having like repeat measurements in the same area for a long time would be really awesome.
Thank you all for weighing in on that and including what's already here that we haven't fully understood yet. Johnny.
Oh yeah. For somebody who doesn't know much about ice-ocean interaction in front of these ice shelves, and we've talked about polynyas, we've talked about atmospheric rivers, and we've talked about circulation, vertical mixing and things. Essentially, I'm asking, do atmospheric rivers ever affect that circulation through the polynya or through the wind shear or whatever?
So I'm thinking of a person in my group that does look at like atmospheric rivers and sea ice, and at least some of what we've sort of talked about within our group, for me, looking at moisture source, looking at different moisture sources from atmospheric rivers, is that that definitely changes seasonally with sea ice and also polynya formation. I don't know that that answers your question, but like, I don't know, some people might know a bit more.
So I don't really know yet, but it's an interesting question. I would say, I mean, there are a couple of axes on which these could interact. So an atmospheric river, there's both the precipitation source, but it's also changing wind fields, yes? And you'll have strong wind fields. So the polynyas that I was talking about and their relationship to vertical mixing is quite dependent on winds. So there's I think there's definitely coupling to be explored on strong short-term wind events. And also the modeling work that I was doing would indicate that some fairly short timescale events could have reinforcing feedbacks that then lead to interannual scale variability. So that's, I guess, another implication that shorter timescale events, whether atmospheric, whether rivers or otherwise, could be involved. But yeah, so I don't know about the seasonality of atmospheric rivers, but I would say wintertime polynya, in wintertime polynya variability is probably more the thing that's going to be important for vertical mixing. But if you dump a whole lot of precipitation in an area from an atmospheric river, that's going to affect the next winter as well. Like, its ability to have vertical mixing. So yeah, given that the precipitation levels are so large, that could be something to explore for sure.
Great, thank you.
So I came up, and then Jamin and Ruth both gave me a great lead-in to this question. And so I saw a bunch of modelers using Sushil's fabulous melt rates, but as a target, that actually gets me worried. I'm a co-author on that paper, and like, I'll sit here and tell you that you should have a little more wiggle room than using a target there with radar altimetry. And Jamin, you brought up the need for high resolution, particularly in a place like Thwaites. But then Ruth just brought up we need wintertime too, and you know the PGC stuff doesn't work in the wintertime. I guess from someone who likes to think about future missions and things like that, from the modelers, like what is the space-time trade-off we need to really start answering these questions to get year-round melt rates at the right spatial resolution to kind of dive into this these modeling, high-resolution modeling questions?
Do you want to go down the line again?
Sure. Yeah, I think not much of my work has focused on super short temporal work, so I think I kind of pass by saying that if you model slower things, I think it would, even though I'm modeling sort of more equilibrium state of my models that don't have these short time term effects, I probably should double check them. So whenever there are more rapid observations to compare against and include in models, I think we definitely should, but I can't speak to it as well as I'd like to yet.
I interpret that as the mission continuity side of the argument.
Yeah, I mean, I'm not super sure, but I guess I would say that to me it seems maybe more feasible that you would have like a couple of example areas that are in distinct thermal regimes, I suppose. So like picking a warm West Antarctic shelf and sticking with that for a little while, and picking a cold shelf area and sticking with that for a little while. Might be, you know, obviously no compromise is a perfect compromise, but that may be one compromise if you're wanting to get, as I think many of us do, some like repeat and high spatial resolution information.
I'll pass because I was only looking at whole ice shelf decadal average melt, so that's good enough for me.
Mission continuity.
Yeah, there you
Yeah, I'm not currently doing a lot of modeling work other than thinking about the isotope-enabled CSM.
Okay. It's tough, right? Because the more we look under ice shelves, the more crazy they look, and the more the melt rate varies by an order of magnitude on the scale of 10 meters horizontally. So then it becomes an average, right? So like, you take the whole section surveyed under Thwaites, and then you take an average, and that's what you shoot for, right? And then you want to know something about seasonal variability, obviously. So then probably you create a semi-regular grid. You put a few AP res out there, and you shoot for the average in like the front of the ice shelf towards the grounding line, over a channel and somewhere else. And then I would say you need at least a seasonal repeat cycle. I can't really think any far past that.
Mission continuity, yes. But I think also, you know, the plan, the new RV, the new ship, supposed to have this polar capability, motivated at least partly for wintertime observations. So that, coupled with the ability to like maintain stations on the ice, like AP res, I think that would be the best complement to the mission continuity for the orbital assets that I can think of.
I don't think I have a great answer for that, because a lot of the stuff that I think about are centimeter to meter scale theory stuff, and I just know that implementing that for long time scales probably isn't really feasible in huge models. And so yeah, I don't have a great answer, except maybe echo something that was said further down the line, that prioritize one spot and stay there for a long time. And so you can section like a specific idea and focus temporal resolution instead of spatial resolution. But not too sure.
Thank you.
Thank you. I see another question waiting on the stairs.
Thanks all for the great talks. My question relates to kind of seasonality, which is discussed in a couple of these talks. And I wanted particularly to learn or hear more thoughts on, given kind of WAIS has been connected to kind of decadal, decadal variability is something that's talked about a lot. And the seasonal imprint, are there observations we should be making that could capture the seasonal cycle, that could kind of help with some of the parameters? I'm thinking of like Priceville or Pinkel models of vertical mixing, like that can improve estimates of sea level change on like century timescales.
I heard enough to know that that was for me, but I must admit I didn't hear it very well. Could you maybe, I don't know, get a little closer to the mic?
Yeah, I'm interested in knowing, so you have like a seasonal cycle that you're looking at, or maybe that's expressed in the model,
Yeah.
that you're, and I'm wondering how that compares, I guess, to the decadal variability that's expressed in observations, and whether there's seasonal measurements that we should be making.
Right, yeah. So yeah, no, definitely a big focus of that modeling work was trying to figure out whether interannual variations in a seasonal cycle essentially could then rectify to a decadal timescale. And the modeling work that we've done at this point, yeah, would indicate that that is plausible for sure. And then in terms of the observations, yeah, because we're wanting, I think this is one of the tricky things, is that it's seasonal variability, but it's interannual variations in seasonal variability. So it's kind of just like I want all time scales for a long time, right? Yeah, but yeah, that's kind of why I think one of big targets in those areas could be moorings that are decently close enough to ice shelves to get some kind of longer term, and also ideally repeat a couple of years to get some seasonal and inter-annual seasonal variation in warm water transport towards ice shelves, which I feel like a decent amount of work is being done in that space already. And then it's the latent heat polynya sea ice formation rates is probably the big one that I feel like there's a lot of data out there that can be used for that, and I just kind of think it's somebody else's PhD, but I would highly encourage anyone, if they want to do a PhD in that, would be great in terms of, I feel like there's satellite products that could be used and that are relatively contiguous to get at both seasonal variations and then year-to-year changes in seasonal variations in sea ice fields. In terms of the actual melt rates from the ice shelf itself, yeah, I haven't thought as much about how, I guess, like the seasonal melt, like, plays into this, or the seasonality in the melt plays into this. Yeah, so I have less to say on that, but I imagine if there is a seasonality in it, then again we have similar possibilities for rectification into longer timescale variability. I hope that answered. Okay.
Oh, we might have a question coming, or someone's escaping the room.
I guess I have a general question to the modelers, especially given the uncertainties in like bed topography, in sub-ice shelf topography with melt channels. Yeah, how robust do you think your models are to this variability? What would you most like to know more, like in terms of constraining melt rate, especially perhaps?
Sure. Yeah, I think that it's something that I'd like to get much more into, but some of the like stochastic approaches that have been used by modelers, both I think to make stochastic estimates and like large ensembles of bed topography to consider in models, and then running models under a variety of different forcings, interacting with all those boundary conditions. And so I think that that's a great approach. I know there's lots of work that's moving towards that. both in Georgia and then Mickey as well in Florida. And so I'm really excited. I think the field's in a really good place to explore a lot more of this stochastic uncertainty. And I hope to be a part of it, but can't really speak to it quite yet. So I think just a lot of ensembles is one way to at least try to quantify our uncertainty in that space.
Yeah, I guess I would second that. Yeah, in my own work, stochasticity comes in both in the ice shelf itself, but also, for example, in convective processes. Convection is a very stochastic process that I ignore the stochasticity of quite conveniently. But yeah, and I would maybe add to that just like a bit of broader context of just like for like ocean modelers, if we're working on kind of regional ocean models and they have an ice sheet, if they have an ice shelf cavity and that cavity is producing thermodynamically interactive melt, that's still like a relatively new thing that we have access to. So that's already like been a massive step. And there is like a huge amount of complexity underlying that we haven't like gotten to integrating. But I think just kind of like maybe like emphasizing that just to keep the kind of, I don't know, timescales of directions, I guess somewhat realistic, that like even just having an ice shelf cavity is far from standard in ocean models, even of high resolutions. And having thermodynamic melt is basically where we're at this point. So yeah, they for example, they're not changing shape at all when they're melting. That's going to be a great step forward, I think, but that's going to take a lot of work. And so, you know, it's kind of one of those questions of like, how much do you add by testing out, I don't know, sensitivity to the draft shape when you're ignoring the fact that the draft is changing in time? I don't know, like, yeah, it's a question as to which one you go after first, and how much going to the intermediate step on your way to the later step is like worthwhile. Yeah. That was a bit rambly, sorry.
I think I might need to stop before it goes down the line, unless somebody at the table is like, no, I've got to say something to that. Okay. We, I believe, are about a minute off lunchtime. Before you erupt into rapturous applause, we're going to have some announcements from Matt, but I just wanted to say these people gave amazing talks that had quite short time windows to them. They know so much more than they had the opportunity to say, even though they've said so much to us today. So talk to them at lunchtime. They seem really nice. Ask the rest of your questions to them in all of the breaks. It'll be rapturous applause and then Matt. So.